Hi there, I'm Mark Chen from OpenAI, and I'm here to present our paper, Generative Pretraining from Pixels. I'd like to start by acknowledging my co-authors, Alec, Riwan, Jeff, Hiwu, David, and Ilya. The goal of our paper was successful unsupervised learning for images. Specifically, we want to learn features that are useful for downstream image classification tasks, without the use of image labels during pretraining. And our approach is generative pretraining using a large transformer. It's worth noting that applying generative pretraining on images isn't a new idea. Methods like deep belief nets and the denoising autoencoder were very popular in the mid-2000s, and they were both motivated by the possibility that modeling the data distribution P of x could aid with the subsequent modeling of P of y given x. However, these types of approaches fell out of favor as supervised methods, which leveraged large labeled datasets, came to dominate image classification benchmarks. Nevertheless, because of the incredible success of unsupervised transformer models on language recently, such as BERT, GPT-2, Roberta, T5, and many others, we believe that this method is due for revisiting in images. We also have a second motivation, in that generative sequence modeling is a general purpose unsupervised learning algorithm. And what I mean here is that any data type can be represented as a sequence of bytes, which means that it can be directly modeled by a sequence transformer without architectural modification. And our work specifically tests the power of this generality by directly applying the same exact architecture that was used to train GPT-2 on natural language to image generation. This also means that we deliberately chose to forego hand-coding any image-specific knowledge in the form of convolutions or techniques like relative attention, sparse attention, or 2D position embeddings. I'm going to take the next few slides to describe our setup. Since we're doing generative pretraining, I'll first start with our pretraining setup. And here we're training an autoregressive objective. Here, in the autoregressive objective, we work with the natural raster order for pixels in the image, and we simply maximize the log likelihood over our training set given this factorization. Later on, we'll also show some results with the BERT objective. And in images, the BERT objective corresponds to masking randomly 15% of the pixels and training our model to recover their contents given the unmasked pixels. It's worth noting here that the BERT model is permutation invariant, or that it has no positional inductive biases. Any spatial relationships between the pixels must be learned by the model at train time. Now, this isn't entirely true for our autoregressive model, because we provide the natural raster order in the factorization. If we were to give a random ordering, it would be a much harder modeling task for the autoregressive model. Next, we'll talk about our evaluation setup. So there are two pretty common approaches for evaluating pre-trained models, and they're the linear probe and fine-tuning. In linear probing, we view our model as a feature extractor. And for our setup specifically, we look at a particular layer, we look right after the layer norm in an attention block at that layer, we average pull across context, and then we use these as features for training a logistic regression classifier. Fine-tuning, which I'm sure many of you guys are familiar with, is where we modify all of the weights within the network, and we view the result of the pre-trained model simply as a favorable initialization for our final classifier that we're learning. The way we set up fine-tuning is pretty similar to the way that we do linear probing. So we take the output after all of the transformer blocks, and then we do a layer norm, we average pull over context, and then we have a linear layer that produces classed logits. One important detail here is that we fine-tune jointly on the generative and classification objectives. And the way we do that is we just simply sum these two objectives. Next, I'm going to talk a little bit about how we consume data. So all of our models are pre-trained on ImageNet. And because of the high computational cost of modeling long sequences with dense attention, we train at resolutions 32 by 32 and 48 by 48. Also, computationally motivated, We use a custom 9-bit color palette instead of RGB. To create this palette, we just simply cluster RGB values that we see into 512 clusters. Now, using this palette yields an input sequence that's almost 3 times shorter than the standard RGB representation, while still encoding color relatively faithfully. You might notice that this breaks permutation invariance of the color channels, but notably, spatial permutation invariance is kept intact. There's also another detail here. Only for linear probe evaluation on ImageNet, we'll train a VQVAE encoder that goes from even higher resolutions, like 96 by 96 or 192 by 192, down into a 48 by 48 latent grid. And this is motivated by trying to capture some of the higher resolution details in ImageNet, which are often important for ImageNet classification. And we use VQVAE because in some sense it's a generalization of k-means. Next, I'm going to talk about the different models that we trained in our work. So we trained models of 3 different sizes, which we'll call IGPT S, M, and L. And they consist of 74 million, 455 million, and 1.4 billion parameters, respectively. It's also important to note their feature sizes, 512, 1024, and 1536. Now, 1536 is pretty comparable to that of a standard ResNet 50, which comes in at 2048 features, though obviously the ResNet is much more parameter efficient. The next few slides I'll be detailing our results. Our first result is that the best features lie in the middle of the network. Because we're training on a next pixel prediction objective, and that this objective is not very clearly related to image classification, it's not clear that features from the last layer of our model should be most predictive of object category. And our first result shows that feature quality is actually a unimodal function of depth. So if you look at this graph, we have on the x-axis the layer in the model, and on the y-axis we have linear probe accuracy on CIFAR10. And we see that the best features lie in the middle of the network across different datasets like STL10 and also CIFAR100. Now, this behavior suggests that a transformer generative model operates in 2 distinct phases. In the first phase, each position will gather information from its surrounding context and contextualize it into a representation. And in the second phase, this contextualized representation is used to solve the conditional next pixel prediction task. This kind of 2-stage performance of our linear probes is reminiscent of another unsupervised neural net, the bottleneck autoencoder, except that the latter is manually designed so that we use the features in the middle. Our next result is that generative performance correlates with feature quality. Here we see a different graph. On the x-axis, we have validation loss, and it's decreasing as we go to the right. And on the y-axis, we have CIFAR10 linear probe accuracy. You'll notice a few lines here, a blue line, a red line, and a green line. And each of these lines tracks a model throughout generative pretraining. These dotted markers that you're seeing are different checkpoints at steps 131K iterations, 262K iterations, 524K iterations, and 1,000,000 iterations. And you can see that these positive slopes suggest a link between improved generative performance and improved feature quality. We also see here that larger models produce better features than smaller models. And this may be due to the fact that the larger models can take advantage of larger width as well. Our third result consists of evaluations on low-resolution classification tasks. So here we include 2 tables from our paper, which detail both performance in the linear probe setting and the fine-tuning setting. So on the left, in the linear probe setting, you can see that we achieve state-of-the-art across the entire spectrum of transfer learning approaches. I want to highlight here CIFAR10 results, where our model achieves 96.3%, which outperforms AMDIM, which is pre-trained on ImageNet without labels, a setting that's equal to ours, and a ResNet 152, which was pre-trained on ImageNet with the labels. Our model is also similarly strong in the fine-tuning setting. We achieve 99% on CIFAR10, which outperforms AutoAugment, the best supervised model trained end-to-end on CIFAR10, even though we don't use sophisticated data augmentation techniques. In fact, 99% ties GPipe, which is the best model which actually pre-trains using ImageNet labels. Our next result is evaluations on ImageNet. There's recently been a resurgence of interest in both unsupervised learning and self-supervised learning on ImageNet. And this motivates us to evaluate the performance of our models using linear probes on ImageNet. Now, this is a very, very difficult setting for us, as we do not train at the standard ImageNet input resolution. Nevertheless, if we look at the performance of a linear probe on IGPT-L, trained at 48 by 48 resolution, we see that we get 65.2% accuracy over 1536 features, which outperforms AlexNet. Now, most contrastive approaches today report their best results on 8,192 features, and it'd be nice to evaluate IGPT at feature parity for comparison. But training such a model is very, very expensive computationally. So we instead concatenate features from different layers within our model as an approximation. One downside is that the features in our model tend to be quite correlated across layers. So we need many of them to be competitive with contrastive approaches. If we concatenate features from 11 layers centered at the best single layer in our 48 by 48 IGPT-L model, we achieve an accuracy of 67.3%. And here's where the VQVAE comes in. If we train a VQVAE from 192 by 192 resolution down to 48 by 48, the same setup bumps our accuracy up to 69%, which is competitive with top contrastive approaches. We also see here that contrastive approaches are more parameter and compute efficient. However, we believe that in showing that an unsupervised transformer model is competitive with the best unsupervised convolutional neural nets, we think this is evidence that it's possible to trade off hand-coded knowledge of a domain for compute. Finally, I want to spend just a minute talking about fine-tuning results on ImageNet. And here, we fine-tune at the low resolutions of 32 by 32 and 48 by 48. Our results are 66.3% accuracy at the low 32 by 32 resolution and 72.6% accuracy at 48 by 48 resolution. Unfortunately, this still underperforms the state of the art, which is achieved by isometric neural nets, which get 70.2% at 28 by 28 resolution. My next result is comparisons with BERT. Because masked language models like BERT have outperformed generative models on most language tasks, we also would like to see how the BERT objective compares in image models. So instead of predicting our model to predict the next pixel, like I described earlier, we're masking out 15% of the pixels and asking our model to recover those. We find that the linear probe performance is significantly worse for BERT models. BERT models actually excel after fine-tuning. We see that a spatially permutation invariant BERT model achieves close to 99% on CIFAR-10 and close to 70% on ImageNet at 32 by 32 resolution. Our final result is in low data CIFAR-10 classification. Here, we're evaluating our model in a slightly more forgiving setting of semi-supervised learning, where we have access to very limited amounts of labeled data. Successful semi-supervised methods today often rely on clever techniques, such as consistency regularization, data augmentation, or pseudo-labeling. Generative approaches in particular haven't been competitive at all for years. We evaluated IGPT-L on a competitive benchmark for this subfield and found that a simple linear probe on features from raw, non-augmented images already outperforms mean teacher and mixed match, though it does underperform the state-of-the-art fixed match. In conclusion, a sequence transformer is competitive with top convolutional neural nets for unsupervised image classification. Simply predicting pixels learns state-of-the-art representations for many low-resolution datasets. And in high-resolution settings, our approach is also very competitive with other self-supervised results on ImageNet. For more details, please refer to our paper. Thank you for listening to my talk.